Welcome to the fourth video in our series on object-oriented programming. Object-oriented programming is when programs are written in terms of objects and classes, and this differs from procedural or functional programming, where programs are written as a collection of functions, or sometimes termed modules. So far in this series, we've learned that objects are unordered collections of properties, meaning data, variables, sometimes termed fields, and methods, by which we mean functions. And therefore properties are things an object has, for example name, age, height and weight, whilst methods are things an object can do, for example run, swim, fly, walk, and so on. We've also learned that we can create blueprints for objects called classes, and that objects can therefore be instances of a class. And when an object is created as an instance of a class, it is said to have been instantiated. An example of objects and classes: Lassie is an instance of the dog class. There are many dogs, but there is only one Lassie, and this is the correct relationship between objects and classes. All of this was covered in much broader detail in the first video in the series, so if you're not confident with these concepts, please check out the first video, otherwise we'll carry on and we'll look at encapsulation. So what is encapsulation? The word encapsulate means to contain. To encapsulate members of an object means to contain them such that they cannot be accessed by external code directly. By external code, we mean code outside the class declaration for that object. When this is done, we say we have implemented a form of encapsulation. Encapsulated members are considered private, whilst non-encapsulated members are considered public. We sometimes refer to the members of an object we can access directly via external code as the object's interface. In this example, we have a me object with the properties first name and last name, and the method walk. In the example pseudocode, we see how we would access members of the me object via external code, i.e. code outside the class declaration for the me object. We can see a very clear correlation between the object's interface and its structure when there is no use of encapsulation. However, if we encapsulate members of an object, we begin to see differences between the object's structure and its interface. In this example, we have encapsulated, or made private, the first name and last name properties, whilst the walk method remains a public member of the me object. The first two lines of pseudocode now no longer work, as they are attempts to access directly members of the object which are encapsulated or hidden from external code. As we just saw in that example, we can have some members private and others public. Public methods can access private members because public methods are within the class declaration and are not external code. The purpose of encapsulation is to protect the properties within an object from being modified by external code, which can result in them containing bad data. So how do we go about protecting members of an object from bad data? Well, instead of allowing direct changes to the properties of an object, we can use a public method of an object to request a change to one of the object's private properties. Methods which handle requests to change an object's properties are often called setters, and methods to retrieve the value of an object's property are often called getters. When we have encapsulated members of an object, and only allow access to those members via public methods, we can define within our methods what happens when there is an attempt to place bad data within an object. The end result of this is that objects are self-policing when they are modified by external code. Now we will look at an example of when we might want to use encapsulation. In this example, we are creating a program to model the solar system. We have a planet class and individual planet objects, for example Mars and Saturn. We want to be able to add new code to the program for new planets if they are discovered, but we do not want it to be possible to create a planet object with bad data. Specifically, we do not want the distance from the Sun to ever be 0. We could also set the condition that we do not want the distance from the Sun value to ever be so high that the planet could not be a member of our solar system. But in this example, for the sake of simplicity, we will concern ourselves only with making sure the value of the planet's distance from the Sun property can never be set to 0. Here is some example pseudocode for our program, which is non-encapsulated. We have the class declaration for the planet class with the property size, mass, distance from the Sun, and the method orbit. And underneath our class declaration, we create an instance of the planet class called Mars. Then we can access the distance from the Sun property of the Mars object and set it to 0. But you'll notice I've put in comments underneath that this shouldn't be allowed. And as we've already said, the most common way of protecting members of an object against bad data is to label the members you want to protect private. The terms private and public are keywords in many languages which support encapsulation. Now we have implemented a form of encapsulation in our pseudocode. We have the class declaration for the planet class, which has the private properties size, mass, and distance from the Sun, and a public method orbit. And still, after the class declaration, we create an instance of the planet class called Mars. Unfortunately now, the distance from the Sun property is completely inaccessible to external code, which is not quite what we want. We want to be able to access it indirectly by way of a public method. In this updated class declaration, I have added the method setDistance, which takes in one argument called distance. And here's the pseudocode for the setDistance method. It takes in one argument, distance, and if the value of distance is greater than 0, then it will set the distance from the Sun property of the object to the value of the argument that was passed. Else, we will output an error message. Error, invalid argument was passed to planet setDistance. Notice that within the setDistance method, we can access the distance from the Sun property, even though the distance from the Sun property is encapsulated, because the code within the setDistance method is also within the class declaration and is therefore not external code and therefore has access to private members of the object. Also notice that if the argument passed to this method is bad data, in this example the number 0, then the distance from the Sun property is not modified. In this example, we would output an error message whenever bad data is passed to this method, but we could do anything we like. We could call a command to end the program, or we could do nothing at all. Now let's create an instance of the planet class called Mars and see what happens when we try to change the distance from the Sun property of the Mars object. In the first line, we try to access the distance from the Sun property directly and assign it to the value of 12. Notice underneath I've put in comments that this won't work. It won't work for exactly the same reason the line underneath won't work. They are both attempts to access private or encapsulated members of the object directly via external code. These first two attempts will most likely result in the program having a compile error. The program won't compile, and our development environment will most likely point us to this line of code and tell us that we cannot access private members of the Mars object. The next two lines use the setDistance method we created. The setDistance method is a public method, and using it will not result in a compile error. But in this example, the argument passed to this method is 0. If we look again at the pseudocode for our setDistance method, we can see that passing the argument 0 to this method will result in an error message being displayed. The advantage of this is that the program will still compile and run, but the object is protected from the bad data, and we can handle attempts to force bad data into the object, like in this example, however we like. The final example is a successful change to the distance from the Sun property of the object. We use the public method setDistance, and we pass in good data, which we know the method will accept, and the distance from the Sun property of the Mars object is then changed to 12. We can see how the use of encapsulation often leads to a common pattern of having all properties private and all methods public. In summary, the advantages of implementing encapsulation are: that if you always use public methods to get and set an object's properties, you can decide to handle failed requests to change or to get an object's property however you like. The logic for how to handle bad requests is kept in the class declaration. This encourages us to think in terms of objects communicating to each other with requests. It reduces the risk of bad data being placed in objects by external code, which otherwise can result in a significant amount of errors when code is updated. And that's it for this video. Please rate, comment and subscribe. Let me know if you enjoyed this video. Let me know if you learned something. In the next and final installment of this series, we'll be looking at the concept of polymorphism, and I hope to see you there.